In this exercise, we will create a ThermoFlo part to study forced convection for internal pipe flows. The user will enter the pipe diameter and length and then chooses the modeling option for the pipe solid wall. The choices are to provide a wall thickness and model the wall as copper, aluminum, or rubber, or alternatively, do not include the wall in the analysis. If aluminum or copper is chosen, we want to use the temperature-dependent material properties from the ThermoFlo library. For rubber, we will use density of 1,000 kilograms per meters cubed, specific heat of 1,500 joules per kilogram C, and thermal conductivity of 0.16 watts per meters degree C. For heat transfer analysis, if the flow is laminar, we want to use the Grates formulation for developing pipe flow, equation 1, with the Grates number given as the product of the Reynolds number and the Prandtl number times the ratio of length over the diameter. For turbulent flow, we would like to use the modern formulation for the Nusselt number, equation 3, where the friction factor for smooth pipe is calculated from equation 4. First, we click on Create Part, and we start a new part, and let's go to Basic, Pipes and Ducts, and we give it a name, Pipe HT for heat transfer. And save. Okay, now that the part file is created, we just go ahead and cancel because we don't want to follow the wizard at this point. Now we just go ahead and open this part that we created. Click on Open Part. We go to where we saved the part, which is in Pipes and Duct, and pipe HT is there. So we double click on that. It opens the part model. So now we go here and we can set an image. Click on that. We go to where we have our images. You could use any image you want. This looks like a good image for a pipe. Use that. And if you choose icon, the part will look like this on your screen. But since this is a pipe, we just use a flow line. Now we need to say where the ports will be. So the first flow port, let's say we want it to go from here, and the second one go to there. And click on Modify. Now let's go ahead and add some user properties for our part. The first one is name. Just change the name to pipe. And always click on Apply Control Changes. Now we add a new property. You need to click on Add User Properties and then make sure that is selected, because otherwise the old one will be overwritten. We call this one L for pipe length. Label would be length on our form, and that's a text box of type length. Let's choose foot and give it a default value of 3. The next one we click on and call it D for diameter. And then we come here and choose length, inch, and give it a value of 2 for the default. This next one is a list box. We want to choose the material. So we say add and we click on it. We call it material. So this will be on the form as a list box called material. And we make sure that we choose list box. Now for each item, you click on Add, make sure it's selected, and give it a name. The first choice is no solid. We don't want to model the material. So that's 0, it's fine. Every time you have to press on Apply. And next one is copper. We have a value of 1 for that. We press Apply. Copper is added to the list box, and go to the next one, add aluminum. That's 2. And that's added. And for the last one, we go ahead and add and give it the name rubber. Rubber is added as item 3. And we have the material selection there. So now we go for a thickness. And we give it the name of pipe THK. This is a variable. And the label is going to be on the form pipe thickness. And we take length, we choose inches, default 0.1, and we continue. The next one is DZ for height change, if you wanted to include that in the analysis. And of course that's length again, and we use a default value of 0 for that. Then the next property, we'll click on it, and this one we say TS. Let's say we want to set the temperature of the solid wall. So we say solid temp, and we go there and choose temperature. C is fine. For the default value, it's convenient to go there and choose the from model parameters we choose ambient. So ambient temperature is now applied by default to the solid. And now we want to have a way of fixing the solid wall temperature. So we add a new user property. We call it, it has to be something that says, you know, if the wall temperature is fixed. So let's see. We could say solid temp fixed. And we go ahead and cut and paste this to the label. That's good for the label. And it's a checkbox. And unchecked, we want it to be 0. Checked 1, and default is fine. We want to keep it unchecked. And the very last property that we want to define, we go ahead and add the number of nodes that we may want to put in analysis. So we just call it nodes. And the label, we call it number of nodes. And this is unitless, and we default value 3, and apply the changes. Okay, now let's design a form layout for these properties that we just created. We click on form layout, and first there's nothing in there, so click on create form layout from user properties, and this will create all of your properties in the order in a form. Now to make it more interesting, you could choose a few properties and put them inside frames. For example, here if we go and choose height change, solid temperature, and if it is modeled, or all of these things, we put them in an advanced frame. So when the user clicks on the advanced frame, these properties will be displayed. So let's go ahead and give it a name. Oops, I forgot the A, so let's put an A in front of the advanced. And this way we have a frame on our form that will display these things. Also note that there are many different ways to change the appearance of the form. You can check on any of these and move it to the top or move it above the selected. Now let's define some tables. The first table we want to define is the whether to include solid or not. So we call it include solid. Now that's going to be a function of material, which is a user property. So we select the user property material and apply. Now we define a step function. Remember, we have 0 means no solid, and then the material could be 1, 2, or 3. So we just allow for 20 materials. We say if it's any of the from 1 to 20, and make it 1. So it's 0 or 1. Now the next table, let's call it AL underscore C sub P. It's aluminum specific heat, a function of temperature of the solid. So we take the solver variable for temperature of the solid. So that's our independent variable. And we need to put columns of temperature and specific heat. If you go to the modeling tab, there is number of solids already there. So we can go and see, yeah, we have aluminum there. So we take the first two sections and we paste it there. So we have the independent variable temperature and C sub P for the aluminum. So that's, we apply that. Now we do the K for the aluminum. The same table, the first temperature stays the same, so we just copy the K values and paste it on top of the C sub P's. And now we have the aluminum K. So now let's go and define copper C sub P. So now if we go to the material, first clear the table, and we go to the material tab and see if we have copper there. So yes, copper is the next one, and we'll take the first two columns and paste that just as before to define the C sub P for copper. And again, after we define that table, we go and change that to K, and we go back to the same table and copy the K values and paste. Okay, now we've defined the K and C sub P for aluminum and copper. And we can check the tables, see if they're defined correctly. Great. And the last one. Now that we defined the table for the aluminum of copper, we can define the C sub P as a new table, which will be function of material. So we go to user properties and we select material. Okay, let's just clear the area. And now we go ahead and we say for 0, that's no solid. If it's 1, 1 means it's copper. So we go to the tables that we just created and we choose the copper C sub P. And 2 should be C sub P for aluminum. And now we go there. So if it's 2, material is 2, we go to the tables and we select aluminum C sub P. Make sure you press apply. And 3 is rubber. We don't need a table for that, so we just use the value that we have, 1500. Apply. Okay, so now we have that. Now let's define the conductivity. Just call it COND, cond. And the same materials. Now the only difference is that we have to change the tables to conductivity tables. So we go back to our tables, and for copper we need the copper's conductivity. Copper K goes here, and this one should be aluminum conductivity. So similarly, we go to our calculator, choose the tables, and we pick aluminum K, select and apply. And for the rubber we go, and we know that's 0.16. There's no temperature dependence. Okay, now we need to define the density. And for density we don't have any temperature dependence, so 0 stays the same. For copper, if you go back to our materials, in copper we had density is 8933, so we just copy that and paste it here for copper. For aluminum, we go again to our table for aluminum in the material, and we copy that and we paste in the correct cell. And for rubber we have 1000 for the density. So that's defined. Again, just to make sure everything is correct, we can go and double check the tables we just created for all the materials. Alright, looks good. Now we need to define the heat transfer properties. So let's go back to our definitions, and we see here that we have a Grates number as the Reynolds number times Prandtl number times L over D, and the friction factor. We need to define these two functions, and then we can take these functions and then use it in another in these other ones for the Nusselt number for laminar and turbulent flow. And I will go ahead and define a function for each one separately, and then we define a table, and the table would be a function of Reynolds number, and we say that if it's less than 2300 we use the laminar, if it's greater than 2300 we use the turbulent. You don't have to do it this way. You could just define the table first and enter the equations for each one, not defining them separately. But if you define them separately, each one, that gives you the opportunity to look at those functions separately when you're debugging or running something. The file that's created keeps track of all your tables that you define. So this way you have more control, and it makes it a little bit easier too. So let's go ahead and define these functions. Okay, now let's go ahead and define our functions and tables. The first thing we want to define is the Grates number, and it's not a function of any user property, so for these cases we just put 1. So that's the function that's defined on its own. So we go there and we choose Reynolds number from the solver variables times the Prandtl number, that's also a solver variable, and we need to multiply that by L over D. So we define, open a parentheses and go to our user properties and take the length, which is L, convert it to meters, and select that and divide it by the diameter, which is another user property. So we take D, and to be consistent we change it to meters again, and we need to now close the parentheses and check the equation in the Matlook. It looks good. Press apply and apply here again to define it. So the next function was the friction coefficient, so we call it fric, and go back to our calculator to define it. Okay, this is slightly more complex, but we start with 1 divided by, there's a quantity square, so we just go ahead and define the parentheses and the square So make sure we don't make a mistake there. And then click inside of the parentheses to enter the values. So it's 1.82. Then we have that times log of Reynolds number. So we go and take log and go to our solver variables to get the Reynolds number. So let's write down here Reynolds number, select, and we need to close the parentheses. Then minus 1.64. Okay, we take a look at the equation. It's consistent and it looks correct. And press apply. And it's entered there, and don't forget to press the apply again. Okay, so with these two defined, now we can define Nusselt numbers first in the laminar regime. So it's Nu sub L for laminar, and we go to our calculator. So this is 3.657, that's the fully developed value, plus the entrance, which is a function of Grates number. So that's 0.0668 times the Grates number. We just defined the table, so we go to our tables and take the Grates number table, which is just a simple function, to the power of 1/3, which is 0.333. And then we need to divide that by, you may open and close the parentheses because we have multiple terms in there. So it starts with a constant 0.04, then plus the same Grates number. Since it's selected already, we just click on that, to the power of negative 0.666. So we need to put a parentheses around the negative sign and the 0.666. And now it looks okay in the window. And apply. Okay, now we need to define the Nusselt number for the turbulent flow and change the name, and we go back to our calculator. Okay, here we have f/8, so we can go and choose the friction factor we just defined, divided by 8. We multiply that by a function of Reynolds number, so it's Reynolds number minus 1000, close the parentheses, times the Prandtl number, which is a solver variable. Then we divide this by 1 plus 12.7 times square root of. So we go and choose square root of, again, f/8, which is friction factor, divided by 8, close the parentheses, times Prandtl number to the power of 2/3, or 0.666, minus 1. Okay, the equation, let's look at it closely. It looks correct. Alright, we press apply and apply again to define the Nusselt number for turbulent. So now that we have defined all the functions, we can define the flow Nusselt number is a function of Reynolds number. So we pick Reynolds number from solver variables. So we go there and we choose Reynolds number, select and apply. So that will be our independent variable. And then we define ranges for that. from minimum to 2300. That's our laminar range. So we go and we select the table we just created for laminar flow. So Nusselt underscore L goes here. And for greater than 2300, so we take a number like 1,000,000, and we apply Nusselt number for turbulent. Again, you could have entered those equations right there, but we define functions to keep track of them. Now we'll define one more function to make our lives a little bit easier for solid area, because we're going to be needing that later on. So I define a underscore solid. Again, it's just 1, and we use the calculator. So this is supposed to be the area for this solid. So that's going to be pi times first the outside area, which is the diameter, plus we make that in meters, and we go and add to the wall thickness. So we take pipe thickness that we had also in meters, squared. So we go outside there and use a square divided by 4. So that's the total area of the pipe, cross-sectional area of the pipe. And now we need to subtract from it the area of the inside area. So we cut and paste that. That's probably the easiest way. And we remove the pipe thickness. Okay, so that's just a simple function that defines the area of the solid cross-sectional area. Now we are ready to assign these to the solver properties. So we go to the solver properties. First, number of nodes. We have a user variable defined for that. So we go to user properties and take nodes. So the user have control over that. And these were 0. So for Nusselt number, we defined the Nusselt number for the flow, which is a function of Reynolds number, and we apply that there. We don't have a user control for heat. The cross-sectional area, we need to enter it over here. So we don't have a user defined for area, but we defined the diameter. So we go, that would be equal to the diameter in meters squared. Oh, I forgot to put the diameter. So let's go back and insert diameter divided by 4. So pi d squared over 4 is our flow area. So wetted perimeter is pi d. So go pi times the diameter in meter. Okay, so, and also for a height change, we had a user property. We left it in centimeters, so we need to change that to meter also. The length, also there is a user variable for that, and we take that, convert it to meters, send it to the solver. The next one is to whether the solid is included or not. And if you remember, we defined a table for that. We go there, include solid. That was our first table based on material properties. So we take that. Now for mass, this is why it was easy to create the solid area. So that's going to be the density of the solid times its volume. So that would be times the table we just created for the solid area. Instead of entering all that stuff, we can just pick that and multiply it by the user property length for the pipe. So that is correct. We apply it there. Specific heat, these were all the tables we created, so we just go and paste them from the tables. This C sub P, apply, and conductivity. Similarly, we have a table for that. Go to tables and you pick the conductivity and apply that there. This we didn't change. Temperature for solid, we have a user control, so we go there to the form and we choose user properties. We go all the way down to T sub S and apply, and then we want to see if the temperature of the solid is fixed. We go to user control. We have a user control for that, and we go down and we choose solid temp fixed. Apply that. Solid area, we created a table for that. That makes the job a lot easier. It's just we choose that from there and apply, and I think that's the last thing we need to set. Now let's go back and take a look at everything quickly, make sure that all the units are consistent, equations look right, and we didn't forget to press apply, and it seems to be okay. Of course, we always need to run a simple model later on to make sure that the part is defined correctly. Okay. Now with that, we've finished with this and we go and save it. We go ahead and save it. And just to have a quick look at what we just created, let's go to another model. And let me set this to the correct size so we can see it easier. And okay, let's refresh the parts, and we go to where we saved that model, pipes and ducts, and here's our pipe that we just created. We drag it on the canvas, double click on it to see our form. Looks like everything is as intended. So we have the materials and advanced tab, and these are the different things that we placed in it. So it looks okay. Let's just go to the part definition, and let's take a look at our tables and functions. So if you go and modify, it shows everything that was defined, and we have everything here. Here's grades number that we defined, along with everything else, and Nusselt number for different ranges of the Reynolds number. So here's our pipe ready to be used.